Everybody dreams of going to Mars, right? It feels like our destiny. But what if I told you that from a fundamental physics standpoint, it's a dream we might never actually achieve? Today, we're going to look at a really powerful argument that says the laws of nature themselves, not our engineering, are the real reason we'll probably never put boots on the red planet. Now, this entire perspective comes from the brilliant theoretical physicist Leonard Susskind, and he makes a really important point right up front. He's not an aerospace engineer trying to figure out how to build a better rocket. No, he's looking at this from the ground up, from the non-negotiable, uncheatable laws of nuclear physics, thermodynamics, and biology. And honestly, his take is pretty sobering. Okay, first things first, we have to get one thing crystal clear. Sending a robot to Mars is a completely different ballgame than sending a person. A rover, it doesn't need to eat, it doesn't need to breathe, and it really doesn't care if its circuits get fried by radiation. But humans, we are incredibly fragile, and that one simple distinction is the root of every single problem that follows. So let's talk about the first huge barrier. And this one is maybe the most fundamental of all. The invisible, inescapable storm of radiation that's just raging through deep space. Here on Earth, we're tucked away safely under our atmosphere and magnetic field. It's like a cozy blanket. Out there, well, there's absolutely nowhere to hide. So just how bad is it? Well, an astronaut on a round-trip mission to Mars would get blasted with up to 250 times the radiation a normal person on Earth gets in an entire year. Let that sink in for a second. That's a massive dose, all packed into just 2.5 years. And this chart really just shows you the insane scale of the problem. That tiny little bar on the left, that's a year of radiation for us here on Earth. That giant bar next to it, that is what we would be asking our astronauts to soak up on a single mission. We're not built for that kind of environment. And, it's not just the amount of radiation, it's the type. We're talking about something called HZE particles. These are not your standard X-rays. As Susskind puts it, they're like microscopic cannonballs. They literally tear through human tissue, leaving these little paths of destruction and shredding DNA in ways our bodies just can't fix. So what does that actually mean for an astronaut's health? Well, NASA's own numbers estimate that the increased lifetime risk of getting cancer is somewhere between 5 and 20%. Now, to give you some perspective, a lifetime of heavy smoking increases your risk by about 10 to 15%. So we would be asking astronauts to take on a cancer risk similar to a lifelong smoker, just from the trip. The obvious solution is shielding, right? Just, build thicker walls. But here is where the physics just gets in the way. To block these particles, you need a ton of mass, literally tons and tons of lead or water, which is just way too heavy to launch. And here's the crazy part. When these super high-energy particles slam into a shield, they can create a shower of secondary radiation inside the ship, sometimes making it even more dangerous. You just can't engineer your way around nuclear physics. And this whole weight problem leads us straight to the second barrier, energy. I mean, getting a massive, heavily shielded spacecraft with all its life support all the way to Mars takes a mind-bending amount of fuel. And it's all thanks to the cruel, unforgiving math of something called the rocket equation. This breaks it down perfectly. The rocket equation is basically a vicious cycle. So you need fuel to push your spaceship, your payload. But that fuel is heavy, so now you need more fuel just to lift the first batch of fuel, and then you need more fuel to lift that fuel. It just keeps compounding until your rocket is almost entirely fuel for the fuel. It's a total exponential nightmare. And I know what you're thinking. What about new engines? Nuclear rockets, ion drives? And yeah, they're more efficient for sure, but they don't break the rules. They are still fundamentally trapped by the laws of thermodynamics. You can't cheat the conservation of energy. It's a hard limit that the universe puts on us. Okay, but let's just pretend for a second. Let's say we could magically solve the radiation problem and the energy problem. We would still be left with the third great barrier, ourselves. The human body evolved for Earth's gravity, and the moment you take that away, it just starts to fall apart. I mean, we have decades of data from astronauts on the International Space Station, and honestly, it's not pretty. They lose bone density at a shocking rate, their muscles waste away, their hearts get weaker, their immune systems get compromised, and some of them even come back with permanent damage to their vision. And that's just from 6 months in low Earth orbit, where they're still kind of protected by our magnetic field. So that brings us to the really terrifying unknown. A mission to Mars isn't 6 months. We're talking about 30 months. That's 2.5 years. Can a human body actually handle that? The honest answer is we have absolutely no idea. And this is the real biological kicker. What happens when you combine that intense, deep space radiation we talked about with years of zero gravity? What happens when you mix those two awful things together? Does the radiation make the bone loss worse? Does a weakened immune system make you way more vulnerable to DNA damage? These are not engineering problems. They're fundamental biology questions, and we can't answer them without taking a risk that is, quite frankly, unethical. So when you start to add it all up, the immense challenges of radiation, the impossible energy requirements, the breakdown of the human body, you arrive at the final and maybe the most impossible barrier of them all, the absolutely astronomical cost. So how much are we talking about? The high-end estimates for a single human mission to Mars, they hover around $1 trillion. That is a 1 with 12 zeros after it. $1 trillion. To put that number in perspective, the entire Apollo program, the program that put 12 men on the moon, the whole one giant leap for mankind's thing, cost about $200 billion in today's money. A mission to Mars could cost 5 times that. And that forces you to ask the hard question. For $1 trillion, what do we actually get? Because from a scientific point of view, robots are just way more efficient. They're cheaper, they're safer, they can stay there for years, and they can collect the vast majority of the scientific data we're looking for anyway. And this brings us right back to Susskind's central point. These aren't just engineering hurdles that we can solve with enough imagination or willpower. These are hard, physical limits baked into the laws of our universe. You can't cheat thermodynamics, you can't cheat the rocket equation, and you definitely can't cheat nuclear physics. The popular analogy is that space is the final frontier, like the American West. But it's not. That was a frontier that was harsh, sure, but it was ultimately a place where humans could live. Space is completely different. It's a vacuum that is actively, constantly trying to kill you in a dozen different ways. It is fundamentally alien to life. So, does this mean we just give up on Mars? No, absolutely not. It just means we should get smarter about it. We should double down on what we know works, sending more advanced, more capable robotic explorers. Let's send robots to drill deep into the crust, to analyze the soil, to search for any signs of ancient life. They could tell us so much more about Mars and our own planet's history than a fleeting human visit ever could. And all of this leaves us with a final, really profound question to think about. Given these immense physical barriers, is it maybe time we start to accept that Earth isn't just our home for now, but for all practical purposes, our only home? Maybe the greatest lesson Mars has to teach us is just how precious and unique this planet we're already on really is.